Compilers don't just turn code into machine instructions, they're designed to solve specific problems. Let's look at the core differences in LLVM and GCC's design philosophies. LLVM is often described as a modular powerhouse, but what does modularity mean in LLVM? LLVM separates its tasks into independent components. The front end translates source code into an intermediate representation, or IR, which is a universal, machine-agnostic form. The middle end optimizes the IR for performance and removes redundancies. And the back end converts optimized IR into machine-specific code, for example, for x86 or ARM architectures. But why is this important? The modularity allows developers to mix and match different components. For example, Apple's Swift compiler uses LLVM's backend, but has a customized frontend specific to Swift's syntax and semantics. Research groups can build custom optimizers for AI models without re-implementing the entire compiler pipeline. This modularity makes LLVM a tool of choice for developing new languages, for example Rust and Julia, or adapting existing ones for novel hardware like GPUs or FPGAs. GCC, on the other hand, is described as having monolithic reliability. So how is GCC's architecture different? GCC integrates all stages of compilation into a single pipeline using tightly connected representations. Firstly, there is GIMPLE, which is a simplified, abstract version of the code for optimization. Then there is RTL, which is low-level architecture-specific representation for machine code generation. But this is confusing, so let's break down GIMPLE and RTL even further. Think of GIMPLE as a shorthand version of your code. It strips away unnecessary details to make it easier for the compiler to improve and optimize the code before creating the final program. And think of RTL, or Register Transfer Language, as a set of blueprints for your computer's hardware. It breaks down the code into instructions that are specific to the processor, for example Intel or ARM, that your program will run on. And these instructions are about moving data between the processor's registers, which are small, fast storage areas, and performing operations on that data so the CPU can understand and execute them efficiently. So RTL is a low-level representation of code that specifies how data moves between hardware registers and how operations are executed on that data. So why does all of this matter? Tightly coupled components make GCC highly efficient for traditional workflows. For example, compiling the Linux kernel, where performance and compatibility with older architectures like x86 are very critical. So GCC's monolithic design shines in environments where stability, speed, and long-term support are priorities. So what is the TLDR here? LLVM is highly modular and adaptable, and it's ideal for building new tools or languages. GCC, on the other hand, is very integrated and streamlined, and it's optimized for established workflows and more legacy systems. How about the whole compilation flow and optimizations? Understanding the compilation process helps explain why each compiler excels in different scenarios. Let's start with the LLVM flow. First, we have the front end. So the front end, for example, Clang for C or C++, parses source code into an abstract syntax tree, or AST, which captures the structure of the code. The AST is then transformed into LLVM IR, which is a universal representation designed for optimization and analysis. Next, we have the middle end, and the middle end performs optimizations on LLVM IR, for example, dead code elimination, which removes unused code, or loop unrolling, which improves loop performance by executing iterations in bulk. And finally, we have the backend, which converts optimized IR into machine code for a specific architecture. For example, LLVM's backend supports exotic hardware like the RISC-V processor, which enables cutting-edge hardware research. In the GCC flow, we have the front end, which translates code into GIMPLE, which is a simpler representation which is designed for optimization. In the middle end, optimizations are applied that are specific to the code and target architecture. For example, GCC may optimize branch prediction for ARM processors, which is critical for embedded systems like automotive sensors. In the backend, GCC will directly generate machine code tailored for the specified architecture, which ensures high performance for traditional systems. For large-scale projects like Android OS, GCC's efficient flow reduces build times without compromising compatibility. Next, we have licensing and industry adoption. So the choice of the compiler can be influenced by how its license aligns with the project's goals. LLVM has a BSD style license, which allows unrestricted use, modification, and distribution, even in proprietary software. And this matters a lot because companies like Apple and Google can use LLVM to build proprietary features. For example, the Swift compiler for iOS or TensorFlow XLA without sharing modifications. So this permissive license encourages LLVM's adoption in closed source ecosystems where innovation without public disclosure is a very high priority. GCC, on the other hand, uses the GPL license. And the GPL requires that any modifications to GCC itself must remain open source. And this has a lot of implications, because it ensures that the open source community benefits from any improvements to GCC. For example, projects like Debian Linux depend on GCC's openness to ensure long-term maintainability and also security. So the TLDR here is that GCC's GPL license is a natural fit for more open source projects, but it almost completely deters companies from using GCC in proprietary toolchains. How about a performance comparison? One thing to note is that performance is not a one-size-fits-all, and it depends on your codebase and your target hardware. So LLVM is more optimized for modern hardware. So LLVM excels at advanced optimizations like auto-vectorization, which involves splitting tasks across multiple CPU cores, and support for heterogeneous computing, for example, using GPUs. An example of this would be TensorFlow XLA, which uses LLVM for its ability to generate efficient GPU code for machine learning tasks. GCC is very legacy friendly, so GCC has faster compilation for traditional systems and has very good support for older architectures. However, GCC struggles because it falls behind LLVM in supporting new architectures like WebAssembly or RISC-V. The choice boils down to whether you prioritize cutting-edge performance provided by LLVM or tried-and-true reliability provided by GCC, the latter being very legacy-friendly. So in summary, LLVM is great for building new languages, targeting modern hardware, and supporting proprietary innovation. GCC, on the other hand, is a very solid choice for open-source projects, more embedded systems, and legacy compatibility. And choosing a compiler is not just about technology, it's also about how it fits into your project's overarching goals and the constraints that it has. If you enjoyed this breakdown and found it helpful, don't forget to like, comment, and subscribe to stay updated with more coding and tech deep dives.